Chapter 7, Introduction to Sampling Distributions. In this video, we'll learn how to calculate the mean and standard deviation for the sampling distribution of a particular sample. We'll also talk about the importance of the central limit theorem, so hopefully you've already watched the bunnies and dragons video that is found in our Chapter 7 resources. So recall in Chapter 2, we learned about frequency distributions, where we'll take the values of a particular distribution and we can graph it to create a histogram. Similarly, when we're working with the sampling distribution, this is where we're going to take the distribution of all possible values of a statistic, say the sample mean for a given sample size that has been randomly selected from the population. In other words, if we took all of the possible random samples of a particular size and calculated the sample mean for each one, and then graphed it in a histogram, we would get a sampling distribution. There are a number of theorems in this chapter that are going to help us work with sampling distributions. While you're not required to memorize these, I'm not going to test on them. It is going to be helpful for you to understand conceptually how sampling distributions work so that when we are calculating or working with sampling distributions, we understand how they operate. So the first theorem is regarding the average value of our sample means. In other words, for any population, if I took all of our possible sample means and I calculated the average value of them, it's going to be the same as our population mean. Because if I'm studying every possible sample in the population, it's the same as studying the entire population itself. So we can write that our mu of our sample mean is the same as our mu of our population mean. Theorem 2 is known as the standard deviation of sample means, also known as our standard error. So if I take all my possible samples and I take their sample means, the standard deviation of these statistics is the population standard deviation divided by the square root of n. Theorem 3 states that if a population is normally distributed, meaning it's bell-shaped, then our sampling distribution of the sample mean is also normally distributed, where theorems 1 and 2 apply. So in other words, we're like combining theorem 1 and 2 as long as our population is bell-shaped. For theorem 4, which you watched a video using the bunnies and dragons as an example, it states that the simple random samples of n observations taken from a population, regardless of the population's distribution, meaning it could be any kind of shaped, it doesn't have to be bell-shaped anymore, provided that the sample size is sufficiently large, then the distribution of our sample means is approximately normal or bell-shaped. Therefore, theorems 1 and 2 still apply. Something to remember is that the larger the sample size, the better the approximation to the normal distribution. You learned about this in the bunnies and dragons video. If you haven't watched it yet, please watch it right now. So this leads us to our central limit theorem. It saves us a lot of time when we're trying to find the probability of an event. Thanks to the previous theorems, when we put them all together, it means that regardless of what our population distribution shape is, it could be uniform, it could be triangular, it could be skewed, it could have multiple modes, that if we have a large enough sample size, our sampling distribution, when I take all my sample means, is going to be bell-shaped. That means we only have to learn one distribution, and that's the normal distribution, as opposed to having to learn all these different shapes. So for the central limit theorem to work though, our sample size must be sufficiently large. If the population is symmetric, then our sample size can be small and it will still provide a normally distributed sampling distribution. This is quite rare though. If our population is highly skewed or irregularly shaped, like we saw in the last slide, then our required sample size will be larger. A conservative definition of what a sufficiently large sample size for means is when n is greater or equal to 30. So think about your Airbnb data. After you clean and organize it and get it down to a sample size for yourself, you want to make sure that you have at least 30 lines of data. However, your files are so large, you should have well more than 30 listings for your analyses. In the last few chapters, we've been converting our x values into z values. Recall we learned about standardizing in chapter 3 originally, and you saw it again in later chapters. So similarly, we can standardize our sampling distribution into z values. Recall a z-value simply measures how many standard deviations a particular value is away from the mean. And so here's our z-value formula, and it'll look very familiar or similar to what we learned in Chapter 6. So here's our sample mean minus our population mean. In other words, this top part right here, that's our sampling error. And here in the denominator, this is our population standard deviation, and we'll divide it by the square root of our sample size. This right here is from Theorem 2. That's our standard error in the denominator. Now the nice thing is once you've found your z-value using this formula, we can then use Excel to find the probability. Let's look at problem 23, very similar to the homework problem. Suppose a population is known to be normally distributed, bell-shaped, with a population mean of 2,000 and a population standard deviation of 230. If a random sample size of 8 is selected, calculate the probability that the sample mean will exceed 2,100. In other words, we want greater than 2,100. So step 1, we want to determine the sample mean we're interested in. And so it's stated right here, we want a sample mean that exceeds 2,100. So that's our starting point. We'll go ahead and write x bar is going to be 2,100. In step 2, we want to define the sampling distribution. We want to make use of our Theorem 1 and Theorem 2 and make sure we pull out the pieces we need for our formula. So our population mean, or our mu, is the 2,000 from the story up here. And for our standard error, that's where we'll take the population standard deviation of 230 and divide it by our square root of 8, because our sample size was 8. So once I take this into my calculator, 230 divided by the square root of 8, we get a standard error of 81.32. Now in step 3, we want to define the event of interest. Recall it said we want to know the probability that the sample mean exceeds 2,100. Exceed is just another way of saying greater than. So the way we'll write our event of interest is our probability of our sample mean is greater than 2,100. Now in step 4, we'll go ahead and plug in everything into our formula to find the z-value of our sample mean. So our sample mean is the 2,100, and our population mean is the 2,000. And then the standard error that we found previously was the 81.32. So again, recall that this top part here, that's our sampling error. That's the difference between our sample mean and our population mean. So I always do this in steps, so in case I make an error, I can go back and see where I made my mistake. So I'd go ahead and subtract these two, and I get my 100 over my standard error of 81.32. When I plug that into my calculator, I get a z-value of 1.23. In other words, 2,100 is 1.23 standard deviations away from the mean. Now you could also, if you jump straight to this formula right here and plug in all the numbers in the right place, you can solve for it. You just want to be very careful that you separate the top sampling error versus the bottom standard error and then divide it as you see here. If you try to plug in top to bottom, then the order of operations is not being followed and you'll get a different answer. So you want to be really careful with that. That's why I set it up this way. In step 5, we'll go ahead and use Excel to find the desired probability. So it helps me to draw the normal distribution curve. So I'll go ahead and map where my z-value falls. This is just a representation, it's not to scale, right? So here's my z-value of 1.23, which is also where the 2,100 would fall. My 2,000 is my mean, that's the midpoint here. And so we want to know, is the event of interest that we identified in step 3 greater or less than the z-value? Because that's going to let us know which side of the curve we're working with. Since we want to know greater than 2,100, we want to know greater than our z-value of 1.23. So we're interested in this area right here. Now recall in Excel though, it reads the probabilities from left to right. So whenever we're working with a greater than statement, we will use the formula based on the complement rule. So that's where we'll take 1 minus, and then here's our probability of the distribution. So we'll do 1 minus norm dot s, because it's already standardized. We standardized our sample mean into a z-value using this formula right here. So we plug in the 1.23, and then comma, and we'll type in true, because it is cumulative, meaning it's adding up all the probabilities to the right of our 1.23. And so Excel will give us 0.1093. In other words, the probability of getting a sample mean greater than 2100 is 0.1093 or 10.93%. So let me go ahead and show you that in Excel. So here are the two formulas that after you've solved the z-value by hand, you can plug that z-value into Excel to find the probability. And it applies for both means and proportions, although in this video we're only talking about means. In the next video you'll learn about proportions. So here I've got my norm.s.dist and then parentheses z comma true. This is when we're doing anything with a less than statement. And here we have our 1 minus norm.s.dist parentheses, I'll plug in my z-value, comma true. This is when we're working with any greater than statements. And if you forget, I have reminders down at the bottom here that tell you when to use true or false and which formula applies for less than or greater than statements. So in that scenario, we were doing greater than 1.23. So I'll type in equals 1 minus norm.s.dist parentheses. I'll type in my 1.23, which was the z-value we found, comma, true, because it's cumulative, and when I hit enter, there's my probability of 0.1093 that our sample mean is greater than 2100. And so if you look to the right here, here's the example we just covered. So you have all the data in here, so you don't have to toggle back and forth between the slides. Now I do provide a formula up here. If you don't want to solve the z-value by hand, you can use Excel using the standardized formula that we learned back in Chapter 3. Except you have to remember that our standard error includes the square root of n. So here's that same problem. If I want to use this formula, and it only works for means, it does not work for proportions. So if I want to solve it using Excel, I'll type in equals standardize parentheses. Now the x is the x value, our sample mean that we're interested in converting. So I'll type in the 2100, comma. The mean, that was the population mean that was given to us, that's the 2000, comma. And then for the standard deviation, in Chapter 7, that's known as the standard error, where we take our population standard deviation, that's the 230, and we divide it by the square root of n. So we'll type in SQRT for the square root, parentheses. Our n in this example was 8, and then we'll close out. And make sure you have enough parentheses to close out your statement. If you don't have enough parentheses, Excel might not give you an answer. So as you can see, I've put in our standard error right here, and then when I hit enter, there's my z-value of 1.23 we did by hand using the formula. So you have the option of finding z-values of a sample mean using Excel, or you can do it by hand. Or you could do both to make sure your answers match and that you're doing it correctly. So if you have any questions, just let me know.